Oh my word. Did you hear? Apparently it's now legal to apply math to your knowledge of electricity and then know even more about it. Times are a-changing. This modern new world with newfangled maths and physics is quite exciting. Of course you'd like to know more about this thing, no? Well, take a seat because it's going to be... Well, you just decide what it's going to be. A couple days ago, Sir George Ohm has written down a new law that helps mathematicians, physics lovers, and stage and lighting engineers calculate three major elements that make up electricity. This law was accepted by governments the world over almost immediately. Normally, laws are written down extensively to try and smooth over anything that can be taken advantage of. Ohm's new law, however, is very simple in both wording and function, and looks as such. U is I times R.
In all seriousness, though, Ohm's law has existed since 1827, and it's really useful. You do well to remember it and to be able to use it, not just because you're going to get a test about it at some point, but also because it's actually really useful. If you're going to do anything with electrical equipment, you do well to know about this law. And if you're going to make stuff that works on electricity, then even more so. But at some point, you're going to have to, connect electrical devices and actually know what you're doing. So here's a start. Ohm's law. As stated, the law reads U is I times R. You'll also see the U as a V sometimes in America. It's the same thing. You'll also find it in this version or in this version. You should be familiar enough with algebra to know that these are the same thing. If you are not, go and learn algebra. It is like learning how to read. Seriously, go do it right now. And then come back. Anyway, that's the equation. Good luck with that. We have some more minutes. Fantasy Watch says I'm out of time. You don't exist. I guess we got some time. If you got time, I'll do some explaining. Here, I've written them down with the U is voltage or spanning, I is current or stroomsterkte, and R is resistance or weerstand. But let's write underneath there, I got my colors, what the units are. And units are eenheden in Dutch. Well, the voltage goes in volts. And the letter is obviously the V. What does this mean? This is how hard we are pushing electrons away. That's what the U comes from. This comes from the Latin word urgere. And urgere means to push. So we are pushing something. Well, what are we pushing? We are pushing the current. We are pushing these electrons. And the amount of electrons we have is the current. And the unit is the ampere or ampere, whatever you want to call it, ampere. And the letter is the A, which is nice. That just works very well. And this is the amount of electrons per second on a given part of the circuit. So you can measure somewhere in a circuit how many electrons are going by. And then you'll have your current. This is not really the unit, electrons per second. It is charge per second, Q over S, but it's close enough for what we want to do here. And for resistance, I don't have enough space here, so this is the letter. It's an ohm, omega, which is the big O sound in Greek. It looks like a horseshoe kind of, And we write it like that. And that's the unit, the ohm. What does this do? Well, it just kind of, stops the current from going through it. The latter is pretty self-explanatory. It's R, it's resistance. It resists stuff. It stops things from going through it, like electricity. But it's how these three variables work together that make the Ohm's law a little bit, weird sometimes. Because electricity, it does behave a little weird sometimes. And we use a lot of metaphors. And we use a lot of different metaphors. And I don't care which metaphor is used. Invariably, they all break down at some point. Because it's a metaphor. It's not actually electricity what we're talking about. We'll be talking about waterfalls or water pumps or slides, whatever. Just keep that in mind when I'm doing this explanation. It doesn't always work. So what always works is the math. That's why you would do well to learn Ohm's law just as a mathematical equation. Learn to work with it because it's useful. Now here I've made a drawing of three people doing some kinky stuff. There's someone that's pushing someone else through what appears to be like a pipe or something, and some other person making life unnecessarily difficult. And you can see I put the letters in there, U or an upside down N, and A, which probably should be an I, but this is the I for current, and this is R, and you should remember that that's these things. So there is someone or something, electrons being pushed by something else, which is the voltage. The voltage is pushing electrons away. And there's some resistance keeping it, in check, if you will. Now what happens if our resistance gets higher? What that means is he's going to pull on that string harder, so this is going to get tighter. So the thickness of the wire of the pipe is going to get smaller, right? So a smaller thickness of a wire means a higher resistance, because these electrons need to be pushed through a thinner cable, if you will. So what happens if he starts pulling harder? Well, either there cannot be as many electrons, this guy needs to slim up a little bit, or we need to push them harder through it. Now what happens if we get a bigger current? This guy gets a little fatter. Well, either our resistance needs to let loose of the string a little bit, or we need to push harder. All right. Now, what if we are getting a higher voltage? What if we are pushing harder? Well, either this guy can get bigger, or this guy can pull harder. So we can either get a bigger resistance or a bigger current, or both in equal amounts or something, to overcome the amount of pushing, the amount of force he's giving. These three are always in a balance. This guy is never going to push harder than he needs to get this guy through. And it's usually this one's the variable, but this is pretty much how it works. Mathematically, this also checks out quite nicely. Let's see. If this one gets bigger, right, we're pushing harder. This one, or both get bigger as well. If R gets bigger, obviously U gets bigger. If I gets bigger, obviously U gets bigger. If our current gets bigger, I gets bigger. Either we need to push harder, or we need to let the resistance go a little bit. And if R gets bigger, well, then we need to push harder because, U gets bigger. Or we need to slim this guy down a little bit if U stays the same. So, this idea, this whole kinky setup, kind of works as a good metaphor. In reality, usually our voltage is a fixed number, 230 for the wall outlet in the Netherlands, or 9 volts for a 9-volt battery. And the resistance usually is also pretty fixed. A circuit has an amount of resistance that it has. And so it's usually the current that changes, which is good to know because you'll be working with currents a little bit more later on. But just know that it's usually the current that fluctuates in circuits, not the voltage or the resistance. It's the current that's the most important variable here. That's the one we're working with. All right, and here's your homework. We have this thing called a short. And we're talking not about lengths here, but about electrical shorts. In Dutch, this is called kortsluiting. And what this means is we have a circuit with no resistance. Now, of course, 0 is not quite possible because there is this cable, so there is a little bit of resistance, but there is no resistor in there. So it, more truthfully, it approaches 0. Now, if R approaches 0, so let's say R is 0.000001, just spitballing here, what happens to our current if this, let's say, is 9 volts? Just stays the same. And remember that if you want to know I'll let you do that one on your own. So, what is I? This is kind of the same thing here. What is I if R becomes really small, arbitrarily small? And question number 2, we also have a thing called a switch. Now, what does a switch do? A switch either has a very high resistance or a very low resistance. And in a circuit, that would look something like this. Now let's just give it a resistance here. So it's not a shorted circuit here. And right now the switch is open. There is no connection between the 2 poles of our voltage. So what is R? Well, ideally it would be infinite. Same question, but now R is not 0, but approaches infinity. What does I become? And how you would calculate this is not by actually putting in infinity, but putting just a very big number. So let's just take just do that. What happens to I? Does that make sense? Probably does. And as always, while I am a licensed physics teacher, this does not make me an expert on the subject. I'm wrong sometimes. Sometimes I know I am, but simplify my explanation at the expense of being completely correct. Sometimes I actually don't know. In either case, I've got a pretty good grasp on the laws of nature and how things work. For the purposes of these videos, the exact correct descriptions of phenomena is not important. I'm trying to give students a new way to look at this world with a technical and logical view. Please feel free to contact me to discuss any of the subject matter within video. Have a good one.